So the last time we met, we started off by looking at, and you did on the whiteboards and on the windows, averages of size 3. So we did samples of size 3, found the averages, you had your 60 data points, you plotted them, and we found, it was last time or 2 times ago, we actually found that that graph looked similar to the raw data graph. All right? And then for this one, it was, all right, now we're doing samples of size 5, and you did that, and you gave it to me here. So what I'm going to do is I'm going to go ahead and take these values, assuming I don't have any errors in my decimal places. And if I go here, stat blue, plot this. This would be n equals 5. I'm going to have my title. What did we end up using as good bin widths? Did we do 25 or 50? 50. Calculate. And it looks more like that. If I go back up and do it with 25, we can see what that looks like. It still looks to be, in that graph, a little right skewed still, but it's less obviously right skewed. So what's slowly happening as we're doing this is the shape is changing a little bit as we have averages. So what I wanted you to contemplate, and do I have the question on here? No. So the question is, why does it make sense that as I increase sample size, the graph itself, because remember the original raw data graph, oh, there it is. The original raw data graph, you see way out here, my high, what was that, like 900 or something? Right, and then we had several in this range, right? But then we were all the way down here. We actually started at 0. But in the one that we just plotted here in class, we're starting at 25 or 50. Now it looks like we're starting at 50. Maybe we're starting at 0. It's hard to tell in there if there's actually a value from 0 to 50. All right, but my maximum now is only 400. It's not 900. So I'm going to switch over to this. LR 204. So the one we were looking here on class was the one that we just created. Now we're going to flip back and look at the one that was, there we go, waiting for it, technology. So this was the original with the raw data. Had a much larger range of values, was very pronounced in its right skewness. The one that we just created with samples of size 5. So the questions that you're thinking of right now, so we can answer here in just a minute, is why does that make sense that it's changing? What is happening when you do the sampling? What's happening with the averages that we're doing? Why is it that the larger the sample size right now, the narrower that graph is becoming? So I'm going to pause, and you're going to think, and then we're going to answer. All right, so like we said, the one thing is the law of large numbers. Law of large numbers says that the larger and larger my sample size, the closer my sample average will be to the actual value. All right? And until you get to the place where, like, if you could actually sample everybody in the population, well, then you would get a census, and you would know that your sample average, even though it's everybody, is the same as your population average, the parameter. And the same holds true for the standard deviation. The larger your sample, the closer your sample standard deviation will be to the population standard deviation. All right. And then secondary to that, then the other reason, or the other thing going on is, as we have a larger sample, we can actually, mathematically, statistically, what we're talking about here, we're reducing variability. A larger sample, when we then create the distribution of all the sample averages, we're actually reducing the variability of that distribution. So what we're going to do is we're going to actually take a look at this website. QR code is up there, so you can scan that. You can do it on your phone if you don't want to do it on your computer. I'm going to pull it up on my computer so we can look at it there. And we're going to do some, this is again, if you wanted to Google search it instead, you could Google search for a sampling distribution applet. is what this is, a sampling distribution applet. I'm going to switch over then back to the computer to show how it's going to work. So for those of you watching online, you'll have to follow along, and I'll do my best to explain as we go. 204. So what I'm going to start with, much like the picture is on the display right now, is a normal distribution as what we're going to call the parent distribution. So this is my parent distribution. This one right here. All right. My parent distribution is this. It's a normal curve. All right. And then what I'm going to do down here is I'm going to change, I'm going to, oh good, that's set at 2. I want this to be set at n equals 2 for the mean. Down here I'm going to do 5 for the mean. So it's going to be similar to what we did before. And what it's actually doing, so I'm going to animate and show you what's going on. Animate, it takes 2 of them and drops that average, takes 5, drops that average. So it did a sample of size 2 and a sample of size 5. And then I'm going to do it again. Does a sample size 2, oh, that was the average. Another random sample of size 5. And it's using a random generating process to sample 2 from this distribution, and it's then making it right here. So that's the average of those 2, and there were 2 of them. And then these are the 2 different averages it did so far for 5. And instead of animating, if I just do a set of 5 of them, you can see, okay, it's going to start plotting. So this is like what we did in class. You took a sample of size 3, and then another sample of size 3, another sample of size 3. You did that 20 times. You talked to 3 classmates. You got 60 of them. All right, so it starts to look about like that. Let's see. There. That's 62 reps. So I did it a whole bunch of times by clicking the 555, and now we have each of these going on. This is the beginning of what's called a sampling distribution. All right, the top one up here, this is actual distribution, up at the top. The next 2 down are the beginnings of a sampling distribution. Why do I say beginnings of? Because a sampling distribution is if I could take, this is the theoretical way, right? If I could take every possible sample of size 2, and then every possible sample of size 5, find the averages for each of them and then plot them, that would be a full sampling distribution. That is almost impossible to do unless you have a relatively finite, small population. But with technology, I can do 10,000. So I click the 10,000. So it just did 10,000 more samples of size 2 for the middle graph, and did 10,000 more samples of size 5 for the lower graph. And when we do that, what shape, how would you describe that middle graph? How would you describe, so again, when we're talking about describing shape, center, spread, and outliers. So again, shape, center, spread, outliers, that the sample of size 2 now is also a normal curve, centered at 15.97, which is about 16. My median is 16 on mine, my sampling distribution, and my standard deviation is 3.56. The standard deviation is smaller than the original. The original standard deviation was 5 up there. The standard deviation of mine down here is 3.56. And then I go down to n equals 5, also appears to be about a normal curve. My center's at 15.98 for the one I did for my 10,062 samples of size 5. And my standard deviation now is 2.26. The standard deviation is getting smaller as sample size increases. Now, it's not the standard deviation of the sample, and here's where I'm going to make some very clear language distinctions as I'm talking. The distributions that are down below are sampling distributions. So when I talk about the average of the sampling distribution will be different than the average of the distribution. Top one, average of the distribution, 16. Second one down, average of the sampling distribution, 15.97. Next one down, average of this sampling distribution, 15.98. If I just say what is the standard deviation, we would be referring to the top graph, which is the parent population. If I say what's the sampling standard deviation, or sampling distribution standard deviation, or the standard deviation of the sampling distribution, or if I say what is sigma sub x bar in this middle one is 3.56. Sigma sub x bar in the bottom one, 2.26. Standard deviation of the sampling distribution is telling us how the spread of those averages is. The standard deviation tells me about the spread of the original data. What do we see as their shapes? What I wanted us to do now, go ahead and clear all those out if you're in this website. All right. And let's change my parent distribution to something skewed. So I selected that drop-down menu and selected skewed. And now I'm going to go ahead and do it the same. I'm going to go, let's do it different. Let's go 5 and 10. And again, you can animate once to see what's going on. It'll randomly select 5. How does it know which one it's going to select? Because this top distribution, most of the data is on the left-hand side, you're going to get more data values that come from the left-hand side just because there's more data down there. And then just because I don't want to waste time, I'm going to go ahead and do 10,000. All right. So if this number is, if that middle one is 5, what shape does that sampling distribution appear to have? Appears to be mostly normal. And this is where, again, as you do more stats, you'll get more comfortable making assessments like that. Instinct would be, at this stage, a lot of people would say, it looks like it's a little right skewed. It's not right skewed enough for me to really worry about it being right skewed. And here's my reason why. Look at the original data. Original data, the mean was 8, the median was 7. In my sampling distribution, my mean was 8.8 or 8.08, and the median was 8. 8.08 and 8 are awfully close together. They're not far enough apart. When I'm talking about 10,000 samples, 10,000 samples should reveal, if there's a big difference, it should reveal a big difference. And it doesn't. It's a very small difference. If I want to, I can do another 10,000. Oh, it got slightly further away than the one I did here in class. 09 versus 0. But they're really, really close. When I get to size 10, I have the same mean, so the mean and standard deviation seems to be about the same difference between them. So these graphs I would call approximately normally distributed, with a mean of 8.09 and 8.09 for both of them, for samples of size 5 and for size 10. And the standard deviation is 2.8 and 1.98. So again, in the previous one, my standard deviations were larger. Again, I'm getting larger and larger samples. I can clear all these out and do it one more time. Oh, and you can make your own. Let's see. Go like that. Let's go like this. There. If I make a really weird looking graph, I could then do, but now I'm going to choose larger samples. We'll have the smaller 110 and the larger 125. And we'll go ahead and animate 10,000 of those. What's happening? Sampling distributions are approximately normal. Which just gets us to, what week are we in? Is this week 7? Sounds about right, doesn't it? We are to week 7 of statistics, and we are now getting to the most important thing about the study of statistics that you're going to learn in this, which is this. The central limit theorem, which we abbreviate CLT. The central limit theorem, I am not going to do the proof of this. So theorem, remember back, so anybody have geometry where you actually had to do like 2-column proofs? Seems like a lot of schools have gone away from 2-column proofs. But a theorem is something that can be proven. All right, you start with some facts, And then from those facts, you can prove a lot of different things. So the central limit theorem is the theorem, like the granddaddy theorem of all statistics. All right. For those of you that have taken calculus, you probably recently in Calc 1 did the fundamental theorem of calculus. And that is the basic principle behind all of calculus. So this one, the proof of the central limit theorem is not fun. And is actually beyond the scope of even an undergrad program in statistics typically. You might spend some time looking at it at a graduate level, but it's pretty complicated. Fundamental theorem of calculus, very attainable, easy to do. Easy, quotes, right? All right, but it says if we collect samples of size n, like we did on that previous slide, right, where we had all of those graphs, a sample of size n. If n is large enough, we'll talk about what that means in a minute. If it's large enough, and we calculate the mean and repeat that many, many times, the histogram of the averages will have an approximate Gaussian curve. Gaussian, normal, bell-shaped. So that is probably the most commonly part of the CLT that gets used. There's a second part. It's a little less, it makes sense when you start to think about it. Similarly, if a sample of size n with a large enough n is taken and the data points are added together. So instead of averaging them, we just add them all up. And that's my one data point. So like we did with the cell phone contacts, instead of averaging them, if you had just taken those 5 and just added them up and that was your one number, and then we graph all of those numbers instead of the averages, it will also start to follow a normal curve. All right? Which, the only difference is in one set, it's just all the numbers added up and they're graphed. In the other one, they're all added up and each individually divided by 5. So they were all just, incrementally shrunk down because they were divided by 5. The top one here is where we're probably going to spend most of our time, but this is... there will be a couple applications where this will make more sense of doing it and will help us to investigate some other principles of the central limit theorem. All right, so here is then our shape. There's my normal curve, and I have a missing tilde. There's my missing tilde. So X bar. So if I were to take all of the averages and graph them, instead of X on the X-axis, I need to make sure that I'm labeling it correctly. Now my X-axis will be X bar. All of the X bars get plotted and put on this graph for the central limit theorem. All right, like the example we did where we did 10,000, right? This is all of them, hundreds and millions and hundreds of thousands of data points that are on here. The middle of this graph is the average of my X bars. So mu sub X bar. And mu sub X bar will be the same as mu sub X. The average of all of the data, if I graphed all of the data, took all the data, found the average of all of the data will be the same as the average of the averages. So the mean, mu, the mean of all X bars will be the same as the mean of all the X data points. All right. And then the standard deviation, and I'm missing also a square root in there. There we go. That's now right. So, and then we do 1, 2, 3, right? 1, 2, 3, 1, 2, 3. This distance from there to there is sigma sub x divided by the square root of n, because that is sigma sub x bar. Notation is very important to make sure you're keeping a difference between the two, because one small little thing, like that little bar right there, difference between sigma sub x bar and sigma sub x is substantial. So being careful that we're using the right things. Of the original parent distribution, the standard deviation is sigma sub x. Sampling distribution, the standard deviation, is sigma sub x bar. And the relationship there, as is written, but I'll make it more formal, sigma sub x bar is equal to sigma sub x divided by the square root of n. If you went back and looked at those sampling distributions you did with that online tool, and you looked at, oh, the original standard deviation was 5, and this one down here was 2.56, and then you took the original one and divided by the square root of 5 or 10 or whatever we took for sample size, they should be about the same number. And it gets that idea. The more and more I sample, I'm reducing the variability of the original graph to a narrower graph that's also still centered on the mean. And the reason why this becomes a fun, so then large enough. We should probably define that. Most textbooks are going to give you the number 30, and that will work. Really only needs to be like about 28, but 30 is good enough. So if I were to do samples of size 30, for any population, no matter what its shape, the sampling distribution will be normal, with an average of all the averages equal to the average of the original, and the standard deviation of that sample, of that sampling distribution equal to sigma sub x over square root of n. So when I say large enough, that'll be the magic number. How large is large enough? 30. And if it is 30, what does that mean? That means the sampling distribution will be normal. So, the parent distribution is the raw data distribution. What we did in class is we had cell phone contacts. But in many cases, I might not know the shape. But again, shape, center, spread, and then outliers are going to be using the z-score formula. Just reaffirming. The mean is mu, the standard deviation is sigma. And that's what we learned at the beginning, before we had to know more means and more standard deviations. But now since we have more of them, I need to specify, this is the mu of x, and that's the sigma of x. And subnotation is of sigma of x, or the standard deviation of x. Okay, and the z-score formula that we used was z equals a data point minus the mean over the standard deviation. And now just to be extra clear, it's minus the mean of x over the standard deviation of x. It should make sense, because if I'm talking about a data point x, then I want to subtract the mean of x from it, and then use the standard deviation of x. When I'm doing my sampling distribution, if n is at least 30, the shape will be normal. The mean of the averages will equal the mean of all x's. The standard deviation of the averages will equal the standard deviation of the x's over the square root of n. And the z-score formula is going to be, now here's what's going to happen. When I'm doing a sampling distribution, remember when we did the animation? It had just a couple data points, and then boop, and then plop down the average. My data now, in a sampling distribution, my data are averages. So if I were to take one randomly selected average, and I'm going to see how that compares to the average of the averages relative to the standard deviation of the averages, which is sigma sub x over the square root of n. Because mu sub x bar and mu sub x are the same, this is often left off as just mu sub x. So here's what this would tell me. This z-score would tell me how far this average is away from my known population average relative to the standard deviation. So it would tell me I am, 1.12 standard deviations above the actual average or the known average. Where we're headed with this, soon but not yet, is once we know this, then we can start making predictions and say, well, what if I don't know this value? because in a lot of cases, we don't know the actual average of something. But if I use proper technique, I can find a good average of my sample and know that this would be the standard deviation of it. And if it follows a normal curve, I can justifiably say, hey, I'm 90% confident that within this interval probably is the actual mean. So then we can start estimating where means are. And as we start entering polling season, you're all registered voters. Hopefully you're voting. You get exit polls, you get things like that, or you see online things like, hey, so-and-so is polling 3 points ahead of so-and-so. All right, and then down really small subscript in the bottom of the screen, it's going to say plus or minus 3%. That's a margin of error. We're going to be getting there pretty soon. You'll be able to understand why that is, and you'll understand that I can make an estimate. If I do a well-done designed a well-designed survey, I can estimate the actual population of the United States outcome within 3%. And I only have to sample about 1,024 people to estimate within 3% how the rest of the entire nation is going to go. And you think, how is that even possible? It's math. All right? So, little flow chart here to get us thinking. If my parent population is normal, then my sampling distribution is normal. If my parent population shape is unknown, if we don't know it, or it's clearly not normal, then I got to look and say, well, how big is my sample size? If my sample size is greater than 30, yes, then my sampling distribution is normal. If it's no, we're going to do a normal probability plot and some other tools and techniques to decide and determine, well, what shape, because you can actually look at your sample. Ooh, I didn't mean to move that. There we go. We can look at my sample. And again, if I have a large enough sample, my sample should mirror the shape of the original population. Maybe not identically, but it should be close. The larger the sample, the closer it should look like it. But we're going to say, well, if this were drawn from a normal curve, so we're going to do this and find out, is it or is it not normal? If it is, then the sampling distribution will be normal. If it is not, we still can't determine its normality, so still not normal. We're going to look at some other things along the lines of symmetry, skewness, and this is where we're going to get into some other tests. So then over here, sampling distribution, if I know sigma is known, we're going to use the z distribution, and that's the one we've been using so far. If sigma is unknown, we're going to use what's called the student's t-distribution, or just the t-distribution. It's called the student's distribution because it was originally published under a pseudonym, because people might not have respected the person who was coming up with the idea because they weren't doing it for the sole purpose of mathematics. They were doing it for the sole purpose of brewing better beer. So if you're familiar with Guinness, you can actually go over there and they have a little emblem for William Gossett. He worked there and he's the one who actually came up with the idea of the student's t-distribution a long time ago. He's dead now. And then the last thing we're going to have that we're going to talk about, this is getting us where we're headed. We're just not completely there yet. All we've done is we've looked at the z distribution, but we haven't connected it to all these other parts yet. But that's where we're headed here in this chapter. Then we're going to do some other work with proportions. Proportions are like a binomial because it's either yes or no. You're either in a proportion or not. And for this, if NP is greater than or equal to 5 and NQ is greater than or equal to 5, we will use the z distribution for that as well. And this will make more sense when we get into some of these examples of that. So if some of this you're just realizing, like, I'm not sure we got to with this. We are starting right here, parent population. When it was normal, we saw that the sampling distribution was normal. If it wasn't, then we did samples up to 30, and then we're over to here. So we're right here. We've got a lot left to cover, but this is where it's headed. And I like a flow chart because it helps to, show the flow of where things are headed, but then also helps with decision-making trees. This flow chart and much other, what goes into statistics is far more than doing calculations. It's usually I wouldn't say that's the least important part, but oftentimes it is. It's, did you choose the right method and the right tool? So much time goes into that, and should, and as we work on problems here, you're going to find that most of the writing that you do will be related to that, related to which distribution are we using? How do we know we're using that distribution? What are the characteristics of that distribution? And then from that, then I'm going to find these two numbers. I'm going to plug it into this equation, or realistically, I'll write the equation down. I'll go online, find a tool, plug the numbers into it. It'll spit me out a number. So actual calculating of things is pretty low. And then you take that response and those numbers at the end and say, and then this is what it means. And you create context for it. Last item is this.